Yo, 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 what's up? So I'm doing your science today. So make sure everyone that is in 9th and 10th grade, or I don't know what grade it is, if it's both, 9th and 10th grade, matter and energy. Okay, hopefully you're doing well. It's good to see you. Well, hopefully see that you're in the stream. I'm just trying to get what we're doing today here momentarily. So just bear with me for a second. Let's see, I have these three, and the first one is 45.
And then check the other two just to be sure.
Is 45, 46.
Are they different, or did they label it different?
Yeah, they're all labeled 46, and then this one's
one?
46 and 40, or 47 and 48. So I didn't know.
Huh. And he's got on here.
I mean, maybe it was supposed to be 45, 46, 47, 48. I don't know.
Well, go back to the first one you have.
And I tried scrolling up. This is all the way up.
Okay, then what about at the very end at the last slide? Can you go to the last slide?
Yep.
Because that'll tell us if the homework matches.
Free page 102 to 104.
That doesn't match either.
Not at all.
So what does it say on here? Oh, that's the wrong one.
This one right here.
Yeah. So what about...
So like maybe they just weren't finished.
Or maybe ask somebody in the class, just ask them what the last note was that they took. Like, or ask them what page they were on, or what, if they know what notes are on.
All right, for those in Matters and Energy Science, just to help me out, what was the last page you guys ended notes on? If someone could throw that in the chat quickly, please.
Yeah, I don't know, because it doesn't match, huh? And are you definitely in Matter and Energy?
Mm-hmm.
Because he had the other ones on there too. Because this says
these
there's no
three.
space, that one you just showed me.
Oh, you are right.
So we need that one.
I might have pressed the wrong one. That might be my fault. There you go.
Lesson 44.
This is probably right.
Okay, that makes more sense then. Look at the last slide.
Thank you for pointing it out. I think that's just a typo. 177 to 120. It's supposed to be 117 to 120, but that looks right.
So that must be the right one.
There we go.
Okay, cool.
Thank you.
I was like, oh man, I don't know what to do.
I just pressed on the wrong one.
Oh, no problem. All right, thanks.
Yep. Because it's all done in PowerPoint. I don't use PowerPoint.
Oh.
So how would I, do you know how do I mirror this one so I can show it to them?
You do.
Or how do you play? Like on mine.
Let me get
on mine, I just on mine I just press play. I don't know how PowerPoint does it.
Because I used that clicker, and then you were able to share screen. But let me see if AJ's available. Be ready to hop back in, okay?
Yep. Let's go. Let's see, guys. Give me a second. Trying to figure this out for you guys so we can get through some of these notes. There we go. I think I got it.
Oh wait, he might have.
I think I got it. I think I'm all good.
Okay, never mind.
All good. Sorry about that.
Okay, thanks.
All right, class, we are ready to begin. Thank you for helping me out, Adrian. I see that help out. Shout out to you. Okay, we're going to get into this. We're in lesson. We're going to be covering page 114 to 116. Okay, so pull out your books. I'm going to be covering the slides. We're just going to be going through the slides. Obviously, I'm not going to be able to teach you to the best of the ability in a sense of maybe Mr. Brown or a specific teacher that studied for this. Okay, but I'm just going to be going through the slides, reading them out loud for you. If you have any questions, okay, you can send them through the chat. I might not be able to answer them. I'll do my best, but we're supposed to get through this lesson, so let's begin. All right, we have 4.1. We're going to be talking about the introduction to energy. Introduction to energy. This class ends at 12:30, so let's try to get through these as quick as we can. Introduction to energy. General fact, okay, energy, number one, is the ability to do work and change matter. Pretty common sense. Again, I'm not really elaborating on them. Once Mr. Brown is back, he'll probably elaborate more. I'm just here to give you guys the notes, you know? I'm just here for that. So I'm trying to do my best. Again, throw your name in the chat so I can know you're here. If you're not here, you will be marked as absent for this class. Okay, so energy is the ability to do work and change matter. Okay, number 2 is the difference between matter and energy. So we're talking about energy and matter. Okay, matter is something that can be seen, touched, or felt, like the physical thing. Okay, energy cannot really be seen or touched or felt. Okay, my body, although energy is going through it, or I can create energy, okay, I'd be consisted as matter. I'm matter. Okay, but I can cause energy. Energy cannot be seen, touched, or felt. If I'm going too fast, just let me know. I don't know if you guys have handout notes or if you're just writing down yourself or how this actually is done for this class. Okay, so I'm doing my best. So if you guys have like, hey, you got to slow down, just let me know. But we're going to try to get through as much as we can in the class period. Number 3, the change of energy. Causes can be observed. Okay, the changes of energy, causes can be observed. We can see the changes of energy. We have things that show us. The changes of energy, causes can be observed. Perfect. Thank you, Sophia, for letting me know. So I can go a little bit faster because that means you guys are just filling in the blanks. Thank you so much. Again, I'm trying. The mic is, they're sketchy today. Maybe it's the wind. Who knows? But they're not working great, so try to follow along the best you can. I'm doing the best I can. Hopefully we can get that working. Hello, hello. All right, there we go. Okay, next one. All changes in matter, whether physical or chemical, require energy. So everything, okay, everything that changes in matter, okay, whether it's physical or chemical, it does require energy to happen. For things to change, it requires energy upon it. Okay, so now we're going to be talking about, those are just some general facts, as you can see. We're going to be talking about some specific things towards energy, dealings with energy. Okay, the SI unit of energy. Number 1, energy cannot be measured directly. It is measured by the amount of change it causes in an object's motion or its physical properties. It cannot be measured directly. Okay, so it's not like, oh, this much energy. Okay, it's more like, okay, it did this much damage or movement, and there's going to be terms that maybe you learn later on what those specific terms are for the different things energy can do. Okay, but energy cannot be measured directly. Energy can be measured by the amount of work it is able to do. Energy can be measured by the amount of work it is able to do. The SI unit for energy, so here's the term you need to know. The actual unit is called a joule. A joule. Joule. The SI unit of energy is a joule, so it's measured in joules. Okay, adding on to that, this joule, okay, or the measurement of SI unit for energy is named after the 19th century English physicist James Prescott Joule. Pretty easy to remember. SI unit of energy is joule. It's named after Joule. There you go. Pretty easy. Okay, so what is a joule? Okay, we know it's the unit of measurement of energy. Okay, but what is it exactly? What does it pertain of? Okay, so here we go. Number 3, letter B. Okay, 1 joule, okay, is the energy required to move an object a distance. Okay, so 1 meter or 39.4 inches. Okay, by pushing it with a force of 1 Newton or 0.22 pounds or of a pound. So 1 joule, so how we can remember it, you don't want to remember the equations. 1 joule equals 1 Newton times 1 meter. Or with abbreviations, 1J or joule equals 1 Newton times or dot 1 meter. So you can throw numbers in there. Okay, you throw numbers in there, you have the same formula. Okay, your numbers would just go in place. So 2 joules would equal 2 newtons times 2 meter, or 2J equals 2N times 2M. Okay, and it looks like our next note, you've learned what a Newton equals. Since 1 Newton equals 1 kilogram times meters over seconds, I'm assuming that is, seconds squared, a joule can also be expressed in terms of the SI base units, meter, kilograms, and seconds. Okay, so not only in other sense 1 joule can equal 1 Newton times 1 meter, okay, 1 joule can equals 1, parentheses, kilograms times meters, divided by seconds squared. Again, okay, they're all 1, so numbers are easy. If you add a 3 for joules, okay, you're adding a 3 in each spot for in your equation. So same thing if we didn't know the joules, so saying how many joules does 4 kilograms over meters times squares or seconds squared, okay, you just plug in the number. So the 4 would be there, you'd multiply the 4 into each thing, okay, and then you would solve your equation and you'd get how many joules. Does that make sense? Someone say yes in the chat if it does, hopefully. Okay, moving on, number 3, letter D. The way that a joule relates to the SI unit of work. Okay, 1 joule of energy is the energy required to do 1 joule of work. Okay, that's pretty easy, right? If we're measuring energy in joules, 1 joule of energy is the energy required to do 1 joule of work. That's pretty common sense. Thank you, Adrian. Okay, so what are some examples of this? Let's get some examples. Okay, examples of understanding how energy 1 joule equals. Okay, letter A. Changing an object's motion requires energy. 1 joule of energy requires or equals energy needed to stop a 2 kilogram or 4.4 pounds object that is moving at the speed of 1 meter per second, or 3.6 kilometers an hour, or 2.2 miles an hour. But just know the 2 kilograms and 1 meters per second. Okay, so 1 joule of energy equals energy needed to stop a 2 kilogram object that is moving at a speed of 1 meters per second. So moving on with this equation. About 4.2 joules of energy are needed to raise the temperature of 1 milliliter of liquid water by 1 degree Celsius, or 1.8 degrees Fahrenheit. So giving you some examples of what joule this reference means. All right, so again, 4.2 joules of energy are needed to raise the temperature of 1 milliliter of liquid water. All right, so we're going to see some forms of energy. Okay, these are the measurements and the units of energy, how we can measure it. The equations, you need to know those. Okay, highlight those in your notes. Okay, what are some forms of energy? Forms of energy. Okay, you should already know them. There's 2 of them, 2 main forms at least. Okay, we have 2 main forms of energy. We have kinetic and potential. Okay, kinetic energy being energy in motion. Okay, that's our normal energy, what we're expelling. Kinetic is energy in motion. Potential energy is a little bit different. It's energy associated with the position of an object and the force acting upon it. Okay, so in the picture, you have an example. Okay, so the biker is going up the mountain. He's expelling energy, kinetic energy, to go up the mountain. Once he's at the top of the mountain, he's not pedaling anymore. Okay, he's kind of in still. But there's potential energy of him going somewhere, right? There's a potential energy. Okay, he's sitting on the mountain or an object, okay, acting as energy. Okay, and as he's going down the mountain, we see kinetic energy again. We're also going to see, so that's number one, two main forms of energy. We're also going to see two forms that energy can be divided into. Two forms of energy can be divided into. The first form is mechanical energy. Mechanical energy. This is energy from forces that affect a whole object. Okay, so as we see in the picture, energy that can be used to do work, it is the sum of an object's kinetic and potential energy. Examples, an elevator, a car, okay? Yes, as of right now, we'll be doing science tomorrow and Friday. Okay, elevator, car, and a hammer in motion. Okay, this is mechanical energy. Energy from forces that affect a whole object. Our second form of energy would be non-mechanical energy. So we have mechanical, non-mechanical. Pretty easy to remember that. Okay, non-mechanical energy is the energy that consists primarily of energy caused by internal motion and forces at the atomic and molecular level. Okay, so like renewable energy through wind currents or solar. Okay, you also have like batteries, how they store energy. Okay, you have different things like a car. Okay, how there's things working inside of a car. It's not actually just going and going. Okay, these are our forms of energy. Okay, so then next, we're going to be looking how energy changes. How does energy change? Okay, so we have these different kinds. We have kinetic and potential. We have mechanical and non-mechanical. Okay, how does energy change? You will send them to Mr. Brown. Okay, again, send them to Mr. Brown. I do not want your science homework, but make sure you send it to him because he is still grading that. Energy changes. Okay, as we have a few more minutes, let's get through these. Energy changes. Okay, number one, two things must happen for properties of matter to change energy. Okay, two things have to happen every single time. Doesn't matter in what situation, two things always have to happen. The first thing, letter A, it must be transferred from one object to another. So the first thing that has to happen for properties of matter to change energy is letter A, it must be transferred from one object to another. Okay, so from matter to change energy, like as we see the bowling pins, okay, it has from one object to another. The bowling ball hits the bowling pins, changing, dropped my phone, changing energy. Wow, the floor is dusty. Okay, secondly, letter B, it must be changed from one form to another. Okay, again, for example, a bowling ball hitting a bowling pin, kinetic energy is transferred from the ball to the pin. Okay, let's look at another example. Letter B, for example, some chemical changes convert an object's thermal or heat energy into chemical energy. Okay, so we have solar energy, right? It's visible light. Okay, it's matter. The sun is matter, yes. Okay, although it's like a gas, it is still matter. Okay, you have solar energy, visible light. You don't have Mr. Brown's email or number. What I would do then, if you don't have his email or number, okay, which it would be on his syllabus, I'm assuming, but if you don't have it, what I would say is, so do all your homework, make sure you keep the sheets of paper you do it on or whatever. Then once you come back in person, or once he's back, he'll let you know what he wants you to do with those. But make sure you have those. So I would say you can turn them in person, okay? Or whenever he gets back, he'll let you know what he wants to do with them, okay? Hopefully that can help you out. Okay, so we see the solar energy going to a chemical, or energy number 1, a tree. Okay, if someone has it, try to share it to some friends or classmates. I'm assuming at least a couple people have it. Okay, then we see it goes another chemical energy to, okay, you have wood that can turn into fire. Okay, so we see another form of this energy transferring from one matter to another. Okay, another example, a flashlight converts chemical energy in a battery to radiant energy or light, right? So you have a flashlight. If you have a flashlight, no batteries, okay, unless some miracle happens, if you keep on pressing the button, okay, to turn a flashlight on, it has no type of battery inside of it to give it power, right? Nothing's going to happen. But when you take another object or matter, put it inside the flashlight, you have one object, batteries. Second object, flashlight. Click the button, and what happens? Light comes out. Okay, so that's a form of energy again. These properties of matter to change energy. Another example. Okay, lots of examples. Okay, someone fires an arrow from a bow. Okay, elastic potential energy is stored in the bowstring. Okay, so the bow can create energy, but it hasn't yet. Okay, it is transferred to the arrow, right? So potential energy in the bowstring, right? You snap a bow. If you ever have shot a bow and arrow, you snap the bow. Okay, it has a potential energy. But when you add another piece of matter or object, like an arrow, into this potential energy of a bow, okay, you can cause, again, a change of energy in the matter. Okay, to the arrow as kinetic energy and to the air as sound energy. You see that in the picture as well. Okay, so now we're going to see the conservation of energy. The conservation of energy. Okay, letter A. In a transfer of energy, the energy lost by one object equals the energy gained by the other. Okay, and you kind of see the food chain there. Okay, you have producers like plants, and you have herbivores that eat plants. Okay, but then you have some consumers, as you see the snake and the mouse, or the rabbit. I think that's a rabbit. Okay, and you have consumers, but then you also have predators above that also eat in that. So that's an example of conservation of energy, the transfer of energy, the energy lost by one object. So obviously when a cow eats grass, taking the energy from the grass, or causing energy from another matter. Okay, we also have, okay, or we're going to see this law of conservation of energy. You'll want to highlight that and know that. Law of conservation of energy. Energy can neither, and this is what this law states, energy can neither be created nor destroyed. I'm sure we've heard that before. Energy can neither be created nor destroyed. Okay, in this law we see two things. First, this law is fundamental to physical science. Second, a consequence of this law is that natural processes cannot create or destroy energy. Okay, this is all with the law of conservation of energy. Let's keep on moving along. Okay, we're almost done. A few more things to get through. Again, I'm sorry I can't elaborate anymore. I'm doing my best. Okay, I'm doing my best. Okay, next we see Albert Einstein discovered, so the conservation of mass and energy. Okay, Albert Einstein discovered that mass and energy can be considered two different ways of measuring, caught my water, the same physical property. Yes, Adrian, I would also suggest turning it in person. Okay, that'd be best, probably for Mr. Brown. Okay, number one, so in Albert Einstein's statement, number one, meaning every object that has a certain amount of energy simply because of its mass. right? We all have a certain amount of energy because of our mass. If you're bigger, you have more energy going on. Although some small people are very sparky, okay, and have a lot of energy, so you're like, is that true? Okay, yes, it is true. Potential energy, not kinetic energy, it has potential energy. Okay, Albert Einstein discovered that mass and energy can be, so same thing. Okay, number 2, adding energy to an object for accelerating it or increasing its temperature slightly increases its mass. Okay, so another thing we're going to see in conservation of mass and energy. Letter B. The relationship between mass and energy is called, and want to know this term, mass-energy equivalence. Okay, and look at the chart for an example. You have kinetic energy as a separate thing, right? Mass is separate and potential energy. They're all separate things. Okay, but when you put them all, and they all end up in the same thing, okay, so you have potential energy, kinetic energy, okay, and then you also have a mass. So something that's doing all three things is this mass-energy equivalence. Okay, and we're going to see an equation that goes with this conservation of mass and energy. Gotta love the equations. Okay, the equation that states the relationship between mass and energy is equation 5.1, which is this. Energy, or E, equals mass times the speed of light, which is represented as C, speed of light. Mass is m. Okay, so you have energy equals mass times speed of light squared. Or, as you see, capital E equals mc squared. Know what each of those mean. E equals energy, m equals mass, c equals speed of light, and the speed of light is squared. Then you have to do order of operations and math, okay, to be able to solve that problem. So here we go. Example. The speed of light is 299,792,458, okay, miles per second. Or, sorry, meters per second, which is about 186 miles per second. It ends at 38 minutes. We're almost done. Okay, so we have, and this is our last note, when mass energy equivalence, so when all those things, kinetic, potential energy, and mass all combine, okay, is accounted for, another law, the law of conservation of energy. And is referred to as, and we need to know this, the law of conservation of mass and energy, which is with that equation we just did. Okay, that is the end of the notes. There is homework for Mr. Brown's class. There's a typo in the homework, but there is homework. Here's the homework. Okay, you have section review 5.1. All of it. Section review 5.1. And you need to read pages 117 to 120. Read pages 117 to 120. So section review 5.1 and read pages 117 to 120. Okay, remember, you're just keeping that. Okay, yes, teachers are. It's not really considered homework per se. It's classwork, especially since you're home. So I guess it would be called homework now because you're all home. Okay, but it will be due when he gets back. Same thing in other classes, okay? It's still due. Okay, you guys are home right now, so there's going to be a little more expectation of participation in getting that work done. Okay, so rather than having a pop quiz, you're just going to have homework. Okay, because it's hard to do a pop quiz with this distant learning thing. So just because a teacher gives you homework and it's Wednesday, okay, yes, it is okay. You're at home all day. Okay, so that's your homework. Session review 5.1. Read pages 117 and 120. If you have any questions, you can ask me. I might be able to help you, okay, or I'll ask Mr. Brown, then I can help you. So you can just text me. I'll help you out with that. Okay, we will see you tomorrow.